All right, so let's look at this problem. This is problem number 5. And then I think, because I did problem 6 in class, I think we should be good. All right, I think we should, I think we've done enough. This is one of the things I don't like about physics is we kill you with sliding blocks. All right, but we're trying to teach you about vectors, and we're trying to teach you about how to add up forces because it's very important. Now, I know your SI, Abby, is probably kind of chuckling going, yeah, this stuff sucks, but it really does get easier. And she's right. Okay, it really does get easier. This is the hardest thing you're going to have to do. Getting the, because what we're doing is we are dismantling all of your misconceptions about how the world works in a lot of ways. Okay, so once we get over this hump, then we'll be fine. All right. Again, I'm probably going to leave this. I'm probably not going to use any numbers. I'm going to make it generic so that it can go on to all kinds of different things. So that all of you can use it with whatever numbers you have. And let's just draw what's going on here. And what do they want us to find a numeric value? Solve numeric for the magnitude of the normal force on the block. Now, look, this normal force is going to be a little bit higher than just mg, even though it's flat, because we got this vector here has two things pushing down on it. Notice it's got a vector coming down, vector going across. All right, so so this vector going down is adding to the normal force. Me and one of your students had a discussion about that today because she was being very honest. She was going, no, wait a minute, that's a negative force. I've got plus the negative, and then when I move it to the other side, it becomes negative, negative, which is positive. Whatever. You can go nuts. I appreciated what she was saying. I saw how she was doing it. She was doing it right, so I just left it alone. All right? Okay, so here we go. We might need the mass. And notice that this force isn't very much, so it's not going to get dominated too much. This force is going to overcome it, even though we've got a kinetic friction here. All right? We got this. We so have this. All right? So here we go. We're going to have to figure out the normal force here. Oh, Jiminy Christmas. I just want these freaking pages to separate. All right, there we go. All right. Let's make that a little bit smaller. I don't know if we need it that small. Let's try it this way. There we go. That's probably good. All right, so problem 5. Here's what's going on. Piece of cake. We got this. We got F1 going like this. We got F2 coming down like this at an angle. Okay, here's the angle theta. And so right away, I'm going to break F2 into its two parts. F2y is going down. F2x going that way. And I know that F2y, the magnitude of F2y, is equal to, it's the opposite leg, so that would be F2 sine of theta. And F2x is equal to, the magnitude of it is equal to F2 cosine of theta. But it's going to have a negative sign in front of it, correct? And I think they gave us the mass of the block is equal to 3.4, so we might need that a little bit later on. I don't think so, but we'll see. Okay, so now, got the mass of the, we've got mg going this way, magnitude of mg, and Fn going up this way. All right? What was the question? Ha! Oh, we want the normal force. And then we want the acceleration. If that angle, and they said, okay, let's say this angle is 30 degrees. Fine. All right, so some of the forces let's just look at the sum of the forces in the y direction. Now we know right away the sum of the forces in the y direction are equal to what? 0. And let's just look. We've got this one, we've got this one, and we've got this one. We've got 3 forces in the y direction. 2 are pointing down, 1's pointing up. The normal force minus mg minus F2 sine of theta. Okay? Oh, so we do need we will need the mass, but they give that to us. All right? So we get the sum of the forces in the y direction is equal to 0. So, I'm just doing it again. So let's solve for the normal force. Well, we're going to bring this guy over and this guy over. So we're going to add mg and F2 sine theta to both sides. And I'm going to wind up with the normal force that was kind of confusing, right? I didn't need that. The normal force is equal to F2 sine theta, which makes sense, the positive of it, plus mg. So therefore, ergo, the kinetic frictional force is equal to that mu of k. They did give us a mu of k in this problem too. Coefficient of kinetic is 0.2. They said mu of k is equal to 0.2, and then times f of n, which would be F2 sine theta plus mg. This is given, this is given, this is given, this is given, and this is a constant of the universe, of the world we live in. All right, so now let's take a sum. So now we want to find the acceleration of this block. All right? I mean, we're done. The rest is just plugging in numbers. The beauty of it's right here. We're done. All right? So now, sum of the forces in the x direction, that's going to equal mass times acceleration in the x direction, which is going to equal, well, it looks like F1's going positive. And we've got a frictional force. I forgot to draw that little F of K up here. Got that little frictional force going this way. So I've got F1 minus F2x. Any other forces in the x direction? Yeah, minus Fk. We know what Fk is right there. Whoa! We're done. So we've got max is equal to F1, which was given, minus F2x is equal to F2 sine theta, and minus mu k times F2 sine theta plus mg. Okay, plus mg. That's an mg right here. And then solve for x. You're going to put all this stuff in brackets. F1 minus F2 sine theta minus mu k F2 sine theta plus mg. Close that off. We've got a number for this, numbers for that, number for that, number for that, number for that, number for that, numbers for that. Divided by m. We got a number for that. You be done. Just add up the forces and go with it. Okay? That's all you got to do. Draw them in, add up the forces. We drew them in. We went and then broke them down into their components. And by reading the problem, we knew that there's a kinetic frictional force. I mean, there's some things that we infer from reading the problem, but we are finished. You guys are going to do great.